In the frozen vacuum of space, 13 billion light-years from Earth, something impossible is staring back at us. The James Webb Space Telescope has peered deeper into the cosmic abyss than any instrument before it, and what it found doesn't just surprise us. It threatens to collapse every theory we've built about how reality works. Ancient galaxies that shouldn't exist, black holes older than time itself, and measurements so contradictory that they suggest our universe might be fundamentally broken. If you've ever wondered whether we truly understand the cosmos, hit that like button, because what I'm about to show you will shatter every comfortable assumption you've ever held about the nature of existence. Prepare yourselves. We begin. The universe is lying to us. For nearly a century, astronomers believed they had cracked one of the cosmos's fundamental secrets. How fast is space itself expanding? The answer seems straightforward. Use distant stars called Cepheid variables as cosmic measuring sticks. Calculate the redshift of galaxies as they race away from us. Apply Einstein's equations, get a number, the Hubble constant, the universe's expansion rate written in kilometers per second per megaparsec. One number that describes how fast the fabric of spacetime stretches across the entire observable cosmos. Then James Webb looked deeper than anyone had ever looked before, and the number exploded into fragments. The universe isn't expanding at one speed, it's expanding at two completely different speeds, depending on where and how you measure it. This isn't a small discrepancy. This isn't experimental error. This is the kind of contradiction that suggests something is profoundly wrong with our understanding of physical law itself. Think of it like playing a video game where the physics engine breaks. You measure your character's speed going north and get one number. You measure it going south and get a completely different number. The game's fundamental rules are inconsistent. Now imagine that game is reality. That's what we're dealing with. The Hubble Space Telescope measured the expansion rate using nearby Cepheid variable stars and got one answer: 73 kilometers per second per megaparsec. James Webb, with its infrared eyes and unprecedented precision, confirmed Hubble's measurements. The nearby universe is expanding at 73 kilometers per second per megaparsec. But when astronomers calculate the expansion rate using the cosmic microwave background radiation, the afterglow of the Big Bang itself, they get a different answer: 67 kilometers per second per megaparsec. Same universe, same physics, two expansion rates. The difference is about 9%. That might not sound catastrophic until you realize what it means. If the universe is expanding at different rates in different regions, or if our measurements are detecting something fundamentally wrong with spacetime geometry, then every calculation we've ever made about the cosmos's age, size, and fate is suspect. Webb didn't just confirm the discrepancy, it made it worse. After observing over 1,000 Cepheid stars across 5 separate galaxies stretching 130 million light-years into space, the contradiction remains. Actually, it intensified. The more precisely we measure, the more wrong our models appear to be. Scientists call this the Hubble tension, but that polite name masks the existential crisis brewing in cosmology. This isn't tension. This is a fracture in the foundation of everything we thought we understood about the universe. Adam Rees, the Nobel Prize-winning astronomer who discovered dark energy and now leads the research into this cosmic contradiction, put it bluntly. With measurement errors ruled out, what remains is the real and exciting possibility that we have misunderstood the universe. Exciting. That word feels wrong when you consider the implications. If our basic understanding of cosmic expansion is incorrect, then the 13.8 billion year age we assign to the universe might be wrong. The 46 billion light-year radius of the observable universe might be wrong. Our predictions about dark energy's influence and the cosmos's ultimate fate might be completely, catastrophically wrong. 3 explanations exist for this crisis, and each one is more disturbing than the last. First, dark energy might not be constant throughout space. The mysterious force that drives cosmic expansion, making up 68% of everything in existence, might behave differently in different cosmic regions. Imagine dark energy like the difficulty settings in a game. In some zones, it's set to easy mode with slower expansion. In others, it's set to nightmare mode with space tearing apart at accelerated rates. If this is true, then the universe isn't a uniform arena playing by consistent rules. It's a patchwork of different physical regimes, each expanding according to its own local laws. The second explanation involves something called early dark energy. Perhaps during the universe's first moments, an additional component existed alongside the dark energy we observe today. This primordial dark energy would have influenced expansion rates in the early cosmos, leaving an imprint on the cosmic microwave background that makes our current calculations incorrect. But here's what makes this possibility so unsettling. If early dark energy existed and then disappeared, it means the universe's fundamental forces can turn on and off. Physical constants might not be constant. The laws of nature might be more like suggestions that the cosmos follows when it feels like it. The third explanation is the most terrifying. Our models of cosmic evolution might be fundamentally, completely, embarrassingly wrong. Everything we think we understand about how matter clumps together, how dark matter influences structure formation, how galaxies evolve, and how the universe transitions from its early hot, dense state to the cool, expanded cosmos we observe today might be built on flawed assumptions. We might be cosmological children playing with toys we don't understand, convinced we've figured out how the universe works when we've barely scratched its surface. But the Hubble tension was only the beginning. While astronomers struggled to reconcile these contradictory expansion measurements, James Webb was making discoveries that would prove even more impossible. Deep in the early universe, in regions of space where the cosmos was only 3% of its current age, the telescope found something that shouldn't exist. 6 massive galaxies, each containing nearly as many stars as our own Milky Way, floating in an epoch when such giants shouldn't have had time to form. Picture this using a gaming analogy. You start a new city-building game, the timer shows you've been playing for 3 minutes, but somehow your city already has skyscrapers, a complete transportation network, millions of citizens and infrastructure that should require hours of gameplay to construct. That's what these 6 galaxies represent on a cosmic scale. They accomplished in 500 million years what should require several billion years of stellar evolution. Astrophysicist Erica Nelson discovered these cosmic anomalies while examining postage stamp-sized sections of Webb's deep field images. She spotted several fuzzy red dots that looked impossibly bright. Red light in astronomy means old light, stretched by billions of years of cosmic expansion during its journey to Earth. But these objects were both ancient and luminous, a combination that defies the laws of stellar evolution and galaxy formation. The team started calling them universe breakers because if these galaxies are real, if they contain what spectroscopic analysis suggests they contain, then our entire understanding of how cosmic structures form needs to be rewritten from scratch. Each of these monster galaxies contains between 10 billion and 100 billion stars. Our Milky Way creates about 2 new stars per year. To reach such enormous sizes in just 500 million years, these early galaxies would need to form hundreds of new stars every single year, for hundreds of millions of years consecutively. The star formation rates required are physically impossible, according to every model we've created. There simply isn't enough time, enough gas, enough gravitational force, or enough dark matter to explain how these galaxies grew so massive so quickly. Think of star formation like leveling up in a role-playing game. You start at level 1. You complete quests. You gain experience points. You gradually, methodically progress through the levels. Now imagine finding a player character at level 100 just 3 minutes after creating their account. Either they're cheating, the game is broken, or there's some mechanism you completely fail to understand. The universe breakers represent that level 100 character. They shouldn't exist, yet they do. Joel Leger, one of the astronomers studying these objects, captured the magnitude of the problem perfectly. We looked into the very early universe for the first time and discovered something so unexpected that it creates genuine problems for science. Not interesting puzzles, not minor anomalies, genuine problems that threaten the coherence of cosmological theory. The discovery suggests that matter in the early universe could clump together and ignite star formation at rates we never imagined possible. But there's something even more disturbing about these universe breakers. They're not alone. Follow-up observations with Webb's spectrograph revealed that massive early galaxies aren't rare exceptions. They're surprisingly common. The early universe appears to have been far more efficient at creating large-scale structures than our models predict. This efficiency problem cuts to the heart of how we think galaxies form. The standard model goes like this. After the Big Bang, matter slowly coalesced under gravity's influence. Small clumps formed first. These small clumps gradually merged to create larger clumps. Over hundreds of millions of years, this process continued, building progressively larger structures until galaxies emerged. It's a bottom-up process, hierarchical and slow. The universe breakers throw this entire timeline into chaos. They suggest a top-down process we've never properly modelled, where massive structures can form quickly and efficiently in the early universe, through mechanisms that remain completely mysterious. The implications extend beyond galaxy formation. If galaxies could grow this massive this quickly, it means dark matter was clumping together at rates far exceeding our predictions. Dark matter, the invisible scaffolding that provides the gravitational framework for normal matter to collapse and form structures, must behave more dynamically and violently than we realized. Perhaps dark matter particles interact with each other in ways we haven't discovered. Perhaps dark matter concentrations in the early universe were far denser and more complex than our simulations suggest. Or perhaps, and this is where it gets truly unsettling, there's a completely unknown force or field operating in the early universe that we've never detected, never modelled, and never imagined. Some mechanism that could rapidly funnel matter into concentrated regions, triggering bursts of star formation that dwarf anything we see in the modern cosmos. If such a force exists, it raises profound questions. Does it still operate today? Can it influence galaxy formation in the current epoch? Or was it a property of the early universe alone, something that emerged from the specific physical conditions present when the cosmos was hot, dense, and fundamentally different from the cold, expanded universe we inhabit now? The universe breakers force us to confront an uncomfortable truth. We don't understand the first billion years of cosmic history as well as we thought we did. That period when the universe transitioned from a smooth, almost featureless state to a cosmos filled with complex structures remains far more mysterious than any textbook admits. And James Webb is revealing just how much we've missed. But massive early galaxies weren't the only impossible objects Webb discovered floating in the cosmic deep. The telescope found something even more disturbing lurking in the universe's childhood, something that challenges every theory of black hole formation we've ever developed. A monster with the mass of 50 million suns, wandering through space completely alone. Deep in the early universe, just 600 million years after the Big Bang, James Webb discovered Q-Sysmond, a supermassive black hole with virtually no galaxy surrounding it. Most supermassive black holes sit at the centers of galaxies like cosmic anchors, surrounded by spinning disks of billions of stars. They form symbiotic relationships with their galactic hosts, growing together over billions of years through delicate dances of gravity, accretion, and feedback. QS-SRN breaks every one of those rules. This cosmic wanderer contains enough mass to equal 50 million of our suns, compressed into a region smaller than our solar system. It's essentially naked, drifting through space, without the typical entourage of stars, gas clouds, and dark matter halos that normally accompany such massive objects. And it exists in the universe's childhood, during an epoch when supermassive black holes shouldn't be possible yet. Here's the problem. Traditional black hole formation requires the death of massive stars. First-generation stars must form from primordial hydrogen and helium. These stars must live their brief, brilliant lives, fusing lighter elements into heavier ones through nuclear processes. Then they must explode in spectacular supernovae, creating stellar mass black holes from their collapsed cores. These stellar mass black holes must then spend hundreds of millions of years gradually accreting matter, slowly growing larger through the painstaking process of consuming surrounding gas and occasionally merging with other black holes. Only after this extended growth period can they become the supermassive monsters we observe at galaxy centers. That timeline requires time. A lot of time. More time than 600 million years. Yet QS-SRN exists, fully formed and supermassive, in an era when the universe barely had time to create its first stars. It's like finding a fully grown oak tree in a forest that's only 3 months old. The tree couldn't have grown that large that fast. Something else must explain its existence. Roberto Maiolino, the Cambridge astrophysicist who helped identify QS-SRN, described it as completely off the scale. 3 theories attempt to explain how QS0n and other naked black holes like it could exist in the early universe. Each theory is more unsettling than the last, and each one requires rethinking fundamental assumptions about how cosmic structures form. The first theory proposes that some black holes form directly from the collapse of massive gas clouds, bypassing the stellar phase entirely. Picture enormous clouds of hydrogen and helium, hundreds of thousands of times more massive than our Sun, collapsing under their own gravity so violently that they form black holes without ever igniting nuclear fusion. These direct collapse black holes would start their existence already massive, giving them a huge head start on growth. But for this process to work, conditions in the early universe must have been far more extreme than our models predict. The gas clouds would need to be protected from fragmenting into smaller star-forming clumps, requiring specific environmental conditions we're still trying to understand. The second theory suggests that intermediate mass black holes, perhaps a few hundred or thousand times the Sun's mass, somehow grew at impossible rates by consuming matter, faster than physics should allow. Every black hole has an Eddington limit, the maximum rate at which it can accrete matter before the radiation pressure from superheated falling gas blows away additional material, is like trying to drink from a fire hose. Beyond a certain flow rate, the pressure becomes too intense. The second theory requires these early black holes to exceed their Eddington limits by factors of 10 or more, feeding at rates that should be physically impossible, but perhaps in the dense early universe, with gas concentrations far higher than anything in the modern cosmos, such super Eddington accretion became possible. The third theory is the most disturbing of all. QS0n might be a primordial black hole, created not from collapsed stars or gas clouds, but from violent density fluctuations in space and time during the universe's first seconds. In the chaotic instant after the Big Bang, before the first atoms formed, before matter and energy separated into distinct entities, the universe was a roiling quantum foam where extreme density variations could exist. Some regions might have been so dense that they immediately collapsed into black holes. These primordial black holes would predate everything. They would be older than the first stars, older than the first atoms, as ancient as the universe itself. If QS0n is a primordial black hole, it means this monster has been lurking in the cosmic darkness since the very beginning. It existed before stars illuminated the cosmos, a black predator waiting in the primordial night. For hundreds of millions of years, it drifted through space until the universe finally evolved enough to create gas clouds and stars that it could consume. Then it began to feed, growing larger as matter finally became available, revealing itself to us only after billions of years of patient existence. But QS0n isn't unique. James Webb has identified hundreds of similar objects, little red dots scattered throughout the early universe, each one a potential naked supermassive black hole defying explanation, each one challenging our understanding of how these cosmic monsters form and evolve. They glow with the light of matter being shredded and superheated as it spirals into their gravitational maws, creating some of the most luminous objects in the early cosmos despite having few or no stars surrounding them. The existence of these naked black holes suggests the early universe was far more chaotic and violent than we ever imagined. Instead of gradual orderly formation of cosmic structures, we might be looking at evidence of primordial catastrophes that forged massive black holes before the first galaxies even began to coalesce. These objects represent a fundamental challenge to the bottom-up hierarchical formation model that cosmologists have relied on for decades. And if primordial black holes really did form in the universe's first moments, the implications extend far beyond explaining early supermassive black holes. Primordial black holes of various masses might still exist throughout the universe today, invisible and undetected. Some could be wandering through our own galaxy, ancient relics from the universe's violent birth that predate every star we can see in the night sky. They could account for some or all of the dark matter that influences galactic rotation and cosmic structure formation. They might be hiding in plain sight, invisible because they emit no light, detectable only through their gravitational effects. But even as astronomers struggle to explain naked, supermassive black holes in the early universe, James Webb made another discovery that would prove even more impossible. The telescope found black holes that don't just challenge our timeline for supermassive black hole formation. These objects challenge our understanding of what came first, the stars or the monsters. Black holes older than the first stars are lighting up the universe, and they might have been there since the moment of creation. Scientists have always assumed a specific sequence for cosmic evolution. First, gravity pulls together clouds of primordial hydrogen and helium. These clouds collapse until they're dense and hot enough to ignite nuclear fusion. Stars are born. The most massive stars live fast and die young, exhausting their nuclear fuel in just a few million years. They explode as supernovae, leaving behind stellar mass black holes. These black holes gradually grow by accreting matter and merging with each other. Eventually, over hundreds of millions or billions of years, some become the supermassive black holes we observe at galaxy centers. That sequence requires stars first, black holes second. But James Webb has found evidence of supermassive black holes existing when the universe was barely 400 million years old, far too early for the traditional formation process to work. The timeline simply doesn't add up. Even if the first stars formed as early as physically possible and immediately collapsed into black holes, those black holes wouldn't have had enough time to grow to supermassive status through normal accretion. Andrea Ferrara and his team at the Scuola Normale Superiore in Pisa, Italy, proposed a radical solution that turns the conventional sequence upside down. What if black holes, not stars, were the first significant sources of light in the universe? What if primordial black holes formed in the chaotic first seconds after the Big Bang and were already lurking in the darkness when the cosmos was still in its infancy, waiting for matter to cool enough to provide them with food? The physics behind this scenario is genuinely mind-bending. These hypothetical primordial black holes would have formed through a completely different mechanism than stellar black holes. Less than 5 seconds after the Big Bang, the universe was an incomprehensibly hot, dense soup of energy and matter, where the boundaries between particles, forces, and space itself were fluid and uncertain. In that chaotic state, extreme density fluctuations could occur, pockets of space where matter concentrated so intensely that it immediately collapsed into black holes without ever forming stars, planets, or any other structure. Picture the early universe as a violently boiling pot. Most of the liquid remains relatively uniform, with small bubbles rising and popping. But occasionally, random thermal fluctuations create regions of dramatically different density. In the cosmic soup, some of these fluctuations would be so extreme that they'd cross the threshold for black hole formation, creating pockets of spacetime so warped that they collapsed into singularities surrounded by event horizons. The evidence Webb has gathered supports this bizarre scenario more strongly than anyone expected. Many of the bright objects in the early universe appear point-like rather than extended, suggesting they're powered by compact sources like black holes, rather than distributed star formation. When gas gets near a black hole, it heats to scorching temperatures before crossing the event horizon, emitting brilliant light from its accretion disk. From our distant perspective, this superheated matter can appear almost identical to the light from billions of stars. If primordial black holes really did form in the universe's first seconds and begin feeding on gas clouds hundreds of millions of years before the first stars ignited, it would explain several mysteries simultaneously. First, it solves the timeline problem. These black holes had a massive head start, forming with substantial masses immediately and spending their first few hundred million years growing larger while waiting for the universe to evolve enough to create stable gas clouds they could consume. By the time the first stars ignited, these black holes were already well on their way to becoming the supermassive monsters Webb observes. Second, it explains why so many early galaxies appear to have supermassive black holes at their centers. In the traditional model, galaxies form first, and black holes grow later at their centers through stellar evolution. But if primordial black holes existed first, they could have served as gravitational seeds, attracting gas and dark matter that eventually formed the galaxies we observe. The black holes wouldn't be products of galaxy formation, they'd be causes of it. Third, and perhaps most disturbing, it suggests that the universe's structure was determined not by the random gravitational collapse of matter, but by the specific locations where primordial black holes happen to form. The cosmic web, the large-scale structure of galaxies, filaments, and voids that fills the observable universe, might be a direct map of where these ancient monsters were created in the first seconds after the Big Bang. But accepting primordial black holes as the first light sources requires confronting deeply unsettling implications. If these objects were common in the early universe, they might still be out there today, invisible and undetected. Some could be wandering through our own galaxy, ancient relics from the universe's violent birth that predate every star, planet and atom we've ever observed. They'd be fossils from an era when the universe operated according to physical laws so extreme we can barely model them. These primordial monsters would represent a fundamental shift in our understanding of cosmic evolution. Instead of a universe that gradually built complexity from simple beginnings, we'd be looking at a cosmos that was born with powerful, massive objects already embedded in its structure, waiting to shape everything that came after. The universe wouldn't be a story of emergence and development. It would be more like a game that starts with powerful NPCs already placed on the map, influencing player behavior and world evolution from the very beginning. The detection of primordial black holes would also provide crucial insights into the physics of the Big Bang itself. The density fluctuations required to create them would reveal conditions in the universe's first moments that we can barely imagine. They'd serve as probes into the Planck epoch, the first 10 to the power of minus 43 seconds, when quantum mechanics and general relativity merged in ways we don't yet understand. Every primordial black hole would be a window into physics at energy scales we could never reproduce in laboratories. But as disturbing as individual naked black holes are, James Webb discovered something even stranger happening in the early universe. Not isolated black holes wandering alone, but cosmic train wrecks creating physics we've never seen before. Two galaxies crashing together in slow motion and suspended between them, defying every law of gravitational stability, a supermassive black hole that shouldn't be able to exist where it is. Astronomers first spotted the object they nicknamed the Infinity Galaxy because of its unusual shape. This cosmic oddity displays two compact red nuclei, each surrounded by glowing rings of superheated gas, creating a perfect figure-8 pattern that resembles the mathematical symbol for infinity. But the galaxy's aesthetically pleasing appearance masks something far more profound and disturbing. The Infinity Galaxy formed when two massive disk galaxies collided head-on millions of years ago. Galaxy collisions aren't unusual. They're actually fundamental drivers of galactic evolution, triggering bursts of star formation and reshaping galactic structures. Our own Milky Way will collide with the Andromeda Galaxy in about 4 billion years, creating a merged elliptical galaxy that astronomers have already nicknamed Milkomeda. But the Infinity Galaxy's collision has created something unprecedented. In normal galaxy mergers, the supermassive black holes from both galaxies eventually spiral toward each other through a process called dynamical friction. As they orbit within the merged galaxy, they interact gravitationally with surrounding stars and gas, gradually losing orbital energy and drawing closer together. Eventually, they either merge into a single, more massive black hole, releasing tremendous gravitational wave energy, or one gets ejected from the system entirely in a gravitational slingshot effect. Both outcomes are well understood and frequently observed. The Infinity Galaxy breaks this pattern completely. The supermassive black hole sits directly between the two galactic nuclei, suspended in a vast expanse of glowing hydrogen gas that's been stripped away from both galaxies during their collision. This positioning should be gravitationally unstable. The black hole should be pulled toward one nucleus or the other, not floating in the middle like a cosmic referee overseeing the galactic crash. Peter van Dokkum and Gabriel Brammer, the astronomers who discovered this system, believe they're witnessing something extraordinarily rare called direct collapse black hole formation. Instead of forming from the death of massive stars, this black hole might be forming in real time from the direct collapse of a massive gas cloud created during the galaxy collision itself. Here's how it works. When two galaxies crash together, they create enormous streams of gas flowing between their cores. Under exactly the right conditions, these gas streams can become so massive and dense that they collapse directly into black holes without ever forming stars. The gas cloud doesn't fragment into star-forming clumps. It doesn't ignite nuclear fusion. It simply collapses wholesale under its own gravity, crossing the threshold where space-time warps so severely that a black hole forms. It's like watching a cosmic avalanche. In normal stellar evolution, matter slowly accumulates over millions of years, building structures gradually. Direct collapse is catastrophic and rapid, like a mountainside giving way all at once. The gas doesn't have time to heat up enough for nuclear fusion. It doesn't form distinct stars. It just falls inward faster and faster until it crosses the event horizon threshold. This direct collapse mechanism could explain one of Webb's most puzzling discoveries: supermassive black holes in the early universe that are far too massive for their age. If black holes can form directly from massive gas clouds, they could start their existence with masses millions of times greater than the Sun, rather than beginning as stellar mass objects and slowly growing through accretion. This massive head start allows them to reach supermassive status much more quickly than traditional formation models predict. The Infinity Galaxy represents a real-time laboratory for studying this exotic formation process. The black hole appears to be actively feeding on gas flowing between the colliding galactic cores, growing larger as the astronomers watch. Radio observations show intense energy emissions from exactly where the black hole should be located, confirming that it's actively consuming matter at prodigious rates. But the direct collapse process raises disturbing questions about cosmic violence during the universe's youth. If galaxy collisions could create supermassive black holes directly from gas clouds, and if galaxy collisions were far more common in the dense early universe, then the cosmos's first billion years might have been dominated by a kind of catastrophic black hole formation we've never properly modelled. The early universe wouldn't have been a place of gradual hierarchical structure formation. It would have been a violent arena where massive black holes could appear suddenly, triggered by the chaotic collisions between proto-galaxies still forming from primordial gas. Hundreds of orphaned worlds are drifting through space in pairs, and they're broadcasting radio signals that shouldn't exist. James Webb has identified over 500 free-floating planets in the Orion Nebula, rogue worlds that don't orbit any star. Each roughly the size of Jupiter, these cosmic wanderers have been ejected from their original solar systems and now drift through the cold emptiness of interstellar space, heated only by their own internal thermal energy and the slow decay of radioactive elements in their cores. But here's what makes them truly bizarre. Many of them travel in pairs, orbiting each other at distances ranging from 25 to 400 times the distance between Earth and the Sun. Scientists call these paired wanderers Jupiter mass binary objects, or jumbios, and they challenge every theory of planet formation we've developed over the past century. Think of planet formation like a crafting system in a survival game. You need specific resources in specific quantities. You need the right environmental conditions. You need time. Planets typically form in the disks of gas and dust surrounding young stars, slowly accumulating material through a process called core accretion. Small particles stick together forming pebbles. Pebbles collide and merge into boulders. Boulders grow into planetesimals. Eventually, over millions of years, these planetesimals become full-sized planets. The gravitational dynamics required to create binary planets add another layer of complexity. For two planets to capture each other and form a stable binary system, they need to be in exactly the right place at exactly the right time with exactly the right velocities. The probability of this happening once is low. Finding dozens of binary pairs in a single stellar nursery suggests that something about our understanding of planet formation is fundamentally incomplete. But the mystery deepened dramatically when astronomers pointed radio telescopes at these paired planets. Several jumbos are emitting radio signals at frequencies and intensities never seen from planets before. These aren't the typical low-energy emissions you'd expect from planetary magnetic fields interacting with charged particles in the solar wind. They're producing gigahertz frequency radio bursts, radiation at frequencies thousands of times higher pitch than FM radio signals on Earth. On Earth, radio signals at these frequencies come from either technological sources like cell phone towers and satellites, or extremely energetic astronomical phenomena like pulsars and quasars. Finding them coming from rogue planets suggests these worlds are experiencing physical processes that don't exist anywhere else in our solar system. The radio emissions appear linked to the binary nature of these planets. When two massive objects orbit each other, they create complex gravitational interactions that generate powerful magnetic fields and electrical currents. Think of it like cosmic friction operating on a scale we've never encountered before. The jumbos are essentially giant electrical generators powered by the gravitational dance of their orbital mechanics. But the signals themselves remain deeply puzzling. Different pairs of jumbos produce different radio signatures, suggesting that each binary system has its own unique electromagnetic personality. Some emit steady streams of radio waves that vary smoothly and predictably. Others produce sporadic bursts that follow no apparent pattern, flashing on and off in seemingly random sequences. A few show what appears to be cyclical behaviour, with emissions that peak and fade on timescales ranging from hours to days. The implications are profoundly unsettling. If these orphaned worlds can generate radio signals this powerful, what else might they be capable of? Their magnetic fields could be orders of magnitude stronger than anything in our solar system. Jupiter has the strongest magnetic field of any planet we've studied, strong enough to create radiation belts that would be lethal to unshielded humans. The jumbos might have magnetic fields thousands or millions of times more powerful, creating space weather phenomena around these rogue worlds that could affect nearby star systems. Even more disturbing is what the existence of so many jumbos suggests about planetary system formation and stability. If hundreds of these paired worlds exist in just one nebula, and if the Orion Nebula is typical of star-forming regions throughout the galaxy, there could be billions of jumbos scattered across the Milky Way. Each represents a failed solar system, a cosmic tragedy, where gravitational interactions went wrong and ejected planets into the eternal night. These rogue worlds are cosmic orphans, forever separated from the warmth and energy of stellar companionship. They exist in perpetual darkness, their surfaces frozen at temperatures just a few dozen degrees above absolute zero. The only heat they experience comes from internal sources, the gradual cooling of their formation heat, the decay of radioactive elements in their cores, and the tidal forces generated by their orbital dance with their companion planet. But the tidal heating from their binary orbits might be more significant than anyone initially realized. When two massive objects orbit each other closely, they deform each other gravitationally, squeezing and stretching in rhythmic patterns. This constant flexing generates heat through internal friction, the same process that keeps Jupiter's moon, Io, volcanically active despite being far from the Sun. The jumbos might experience similar tidal heating, potentially maintaining liquid layers beneath frozen surfaces, or driving atmospheric processes powered entirely by orbital mechanics rather than stellar radiation. The radio emissions could even indicate atmospheric auroras, electromagnetic phenomena similar to Earth's northern and southern lights, but operating at energy levels that would be lethal to any known form of life. If the jumbos have atmospheres rich in hydrogen and helium, their powerful magnetic fields could interact with charged particles to create spectacular auroral displays that emit radio waves detectable across interstellar distances. But as disturbing as these wandering radio broadcasting planets are, Webb discovered something even stranger in a young star system where the basic chemistry of planet formation has gone catastrophically wrong. A planetary disk where the wrong molecules dominate, creating worlds unlike anything in our solar system. We're not looking at the universe's youth. We're looking at a crime scene where the laws of cosmic evolution have been violated in ways we're only beginning to understand. In the star-forming region known as NGC 6357, James Webb discovered a planet-forming disk that contains almost no water but is rich in carbon dioxide, exactly where Earth-like planets should be forming. This finding shatters one of the most fundamental assumptions about how rocky planets develop around young stars. Every model of planetary formation we've ever created assumes that the regions around young stars where terrestrial planets form should be dominated by water ice and silicate minerals. Water is one of the most abundant molecules in the universe. Oxygen readily bonds with hydrogen, creating H2O molecules that freeze in the cold outer regions of protoplanetary disks and evaporate in the warmer inner regions. This water ice, along with rocky silicates, provides the building blocks for worlds like Earth, Mars, and Venus. The disk around the star Zu-10 throws all of these assumptions into chaos. When Webb examined this system using its near-infrared spectrograph, astronomers expected to see the familiar signature of water vapor mixed with silicates, carbon monoxide, and other common compounds. Instead, they found a disk where carbon dioxide dominates the inner regions, the exact zones where terrestrial planets typically form. Water is so scarce that it's barely detectable, creating a chemical environment unlike anything we've seen before or properly modelled. This discovery challenges everything we understand about planetary formation chemistry. On Earth, water played a crucial role in creating our planet's geology, atmosphere, and ultimately the conditions that allowed life to emerge. Liquid water acted as a solvent, enabling chemical reactions that wouldn't occur in dry environments. Water vapour in our early atmosphere created a greenhouse effect that kept the surface temperature stable. Ocean water provided the medium where the first self-replicating molecules assembled themselves into primitive life. A planet forming in the XUE-10 system would develop under completely different chemical conditions. Instead of water-rich chemistry driving geological and atmospheric processes, carbon dioxide would dominate. The planet's surface might be coated with carbonate minerals rather than silicates. Its atmosphere, if it retained one, could be thick with CO2, creating a runaway greenhouse effect more extreme than anything on Venus. Volcanic outgassing would release carbon dioxide rather than water vapour, further altering the atmospheric composition. Two theories attempt to explain this bizarre chemistry, and both have deeply unsettling implications for the diversity and habitability of planets throughout the galaxy. The first suggests that intense ultraviolet radiation from either the young star itself or from massive nearby stars has essentially sterilised the disk. UV photons are energetic enough to break apart water molecules, splitting H2O into hydrogen and oxygen. The lightweight hydrogen atoms escape the system entirely, driven away by stellar winds and radiation pressure. The remaining oxygen atoms combine with carbon to form carbon dioxide, which is more stable under UV bombardment. If this sterilisation process is common around young stars, it means that many potentially habitable worlds might never get the chemical building blocks they need for life as we understand it. Stars more massive than our Sun emit intense UV radiation. Stars in crowded stellar nurseries bathe each other in UV light. The galaxy could be filled with dry, carbon dioxide-rich planets that formed under conditions hostile to water-based chemistry. The second theory is even more disturbing. The carbon dioxide dominance might result from unusual conditions in the dust grains that make up the planetary disk. Normally, dust grains in protoplanetary disks are coated with water ice in the cold outer regions and remain dry in the warm inner regions. But in the XUE-10 system, the dust grains might be covered with carbon dioxide ice due to specific environmental conditions around this young star. If the carbon dioxide coating is thick enough and stable enough, it could prevent water molecules from sticking to the dust grains. Without water ice coating the grains, the process of planet formation would proceed using entirely different materials. The planets would inherit the chemical composition of their building blocks, resulting in worlds rich in carbonates and poor in water. Either explanation suggests that planetary formation can follow pathways astronomers never imagined. The diversity of planet types might be far greater than we've ever considered. We've been searching for Earth-like planets, worlds with liquid water and oxygen-rich atmospheres. But the universe might be filled with carbon worlds, silicate worlds, metal worlds, and exotic types we haven't even conceived yet. Each class would form through different chemical processes, develop different geological and atmospheric characteristics, and offer different possibilities for life. The XUE-10 system represents a natural laboratory for studying alternative planetary formation pathways. As the planets in this system continue to develop over the next few million years, they'll provide insights into how worlds form when the basic chemical ingredients are fundamentally different from what we see in our own solar system. These dry, carbon dioxide-rich planets might harbour forms of life using completely different biochemistry, or they might remain forever sterile, examples of how a slight variation in stellar environment can prevent worlds from ever becoming cradles for living organisms. But as troubling as these dry worlds are, they represent just one example of the atmospheric mysteries Webb has uncovered. The telescope's next target would reveal a world whose atmosphere shouldn't exist at all, yet somehow persists despite conditions that should have stripped it away billions of years ago. A world so close to its star that its surface glows like molten metal somehow maintains an atmosphere that defies every law of planetary physics we've established. 55 Cancri e orbits its star so closely that it completes a full year in just 18 Earth hours. This hell planet is tidally locked, meaning the same side always faces its star, creating a day side hot enough to vaporize rock, and a night side plunged into eternal darkness. Surface temperatures on the day side reach over 4,000 degrees Fahrenheit. To put that in perspective, that's hot enough to melt copper, brass, and many types of steel. The planet's surface might be an ocean of liquid lava, with minerals boiling off the surface and raining back down on the night side as solid rock. By every rule of planetary physics we've developed over decades of studying solar system bodies and exoplanets, this world should have lost its atmosphere billions of years ago. Planets close to their stars face intense stellar radiation and powerful stellar winds that strip away atmospheric gases over time. Mercury, the closest planet to our Sun, lost most of its atmosphere eons ago, leaving behind only a thin exosphere of particles kicked up by solar wind impacts. Venus, with its thick atmosphere, survives only because it orbits far enough from the Sun that atmospheric erosion occurs slowly. Mars lost most of its atmosphere after its magnetic field shut down, allowing solar wind to strip gases directly from the upper atmosphere. 55. Cancri air should be like Mercury, essentially airless despite being much more massive. The stellar radiation it experiences is thousands of times more intense than anything Mercury endures. Yet James Webb discovered the impossible. This hell planet not only has an atmosphere, but it's composed of materials that shouldn't be able to exist as gases at such extreme temperatures. The atmosphere appears rich in carbon monoxide and carbon dioxide, creating a thick blanket around a world that should be as naked as Mercury. Webb detected these atmospheric gases by carefully measuring the thermal emissions from the planet's day side. When the planet passes in front of its star from our perspective, the combined light includes both stellar radiation and thermal emissions from the planet's superheated surface and atmosphere. When the planet passes behind its star, only stellar light reaches us. By subtracting one measurement from the other, astronomers isolated the planet's thermal signature. That thermal signature revealed something stunning. The day side is cooler than it should be given its proximity to the star. Something is blocking and redistributing the star's heat, transporting energy from the scorching day side to the frozen night side. That something could only be an atmosphere thick enough and dynamic enough to drive global circulation patterns. Think of this atmosphere like the cooling system in a high-performance gaming computer that's constantly on the verge of overheating. The components generate tremendous heat that would cause catastrophic failure if not continuously removed and dissipated. The cooling system uses fans, heat pipes, and radiators to transport that heat away from critical components and dump it into the environment. The Hell planet's atmosphere serves a similar function, but on a scale that makes engineering solutions look primitive. The discoveries we've explored so far, impossible galaxies, premature black holes, planetary anomalies, represent cracks in cosmology's foundation. But they're symptoms of something deeper, something more fundamentally wrong with our understanding of the universe's structure and evolution. James Webb isn't just finding objects that shouldn't exist. It's revealing that the processes we thought we understood, from galaxy formation to atmospheric retention, operate according to principles we've never properly grasped. Now we descend deeper into the cosmic abyss, into regions where space-time itself becomes unstable, where objects form through mechanisms that break every rule, where the line between possible and impossible dissolves into quantum uncertainty. The first act revealed that our models are broken. The second act will show us why reality itself might be breaking down. An ancient comet from another star system is racing through our solar system, and it's older than Earth, the Sun, and everything we call home. Comet 3I Atlas appears unremarkable at first glance, just another icy wanderer passing through our cosmic neighbourhood. It's about 7 miles wide, composed of ice, rock, and complex organic molecules accumulated over billions of years in the frozen outer reaches of some distant stellar system. But James Webb's detailed spectroscopic analysis revealed something that challenges our understanding of cometary composition and galactic dynamics. This interstellar visitor is approximately 7 billion years old, making it 3 billion years older than our entire solar system. When astronomers tracked the comet's trajectory and reconstructed its path through the galaxy, they realized it originated from the Milky Way's thick disk, a region filled with ancient stars that formed when the universe was much younger and had dramatically different chemical composition than the modern cosmos. This cosmic wanderer has been drifting through interstellar space since before our Sun was even a glimmer in a molecular cloud. It predates Earth, Mars, Jupiter, and every planet in our neighbourhood by billions of years. The comet existed when the Milky Way was more chaotic and violent, when star formation rates were higher and supernova explosions were more frequent. It's a time capsule from an era we can barely reconstruct from observations. Webb's near-infrared spectrograph revealed that the comet's coma, the cloud of gas and dust surrounding its nucleus, is dominated by carbon dioxide rather than the water vapour typical of comets from our solar system. This unusual composition provides crucial clues about the chemical environment of the star system where it formed. 7 billion years ago, stellar nuclear synthesis had produced less oxygen relative to carbon than in the modern universe. The ratio of different elements was shifted toward lighter, more volatile compounds. The comet's chemistry is literally alien, reflecting the conditions of a younger galaxy. The comet travels at over 130,000 miles per hour relative to our solar system, fast enough to cross the entire United States in less than 2 minutes. Its trajectory is unusually flat and straight, unlike the elliptical or parabolic orbits of objects bound to our Sun. This interstellar intruder follows the gravitational rules of the galaxy rather than our Sun, treating our entire solar system as just another gravitational perturbation to navigate around. What makes this ancient visitor truly unsettling is what it represents beyond its own existence. 3I Atlas is a messenger from a time when the universe was radically different. 7 billion years ago, when this comet formed, the Milky Way was less than half its current age. Star formation was proceeding at much higher rates. The galactic disk was thinner and denser. Heavy elements were scarcer because fewer generations of stars had lived and died to enrich the interstellar medium with the products of nucleosynthesis. The comet formed around a star that lived and died billions of years before our Sun existed. That parent star could have been similar to our Sun, a stable yellow dwarf that hosted a planetary system for billions of years, or it could have been more massive, burning through its nuclear fuel in a few 100 million years before exploding as a supernova. Either way, something catastrophic happened to that ancient solar system. Some gravitational perturbation, perhaps a close encounter with another star or a passing molecular cloud, ejected the comet from its original orbit and sent it wandering through the galaxy. For 3 billion years it travelled through the cosmic deep, a frozen time capsule carrying chemical signatures from an ancient epoch. It drifted through spiral arms and ventured into the galactic halo. It witnessed the birth and death of countless stars, passing within light years of planetary systems that formed and evolved while it continued its lonely journey. The comet saw more of the galaxy's history than any observer could experience, crossing vast expanses of space that our civilization will never reach. The fact that we're seeing it now raises disturbing questions about how many other ancient visitors might be passing through our solar system undetected. 3I Atlas is only the third confirmed interstellar object ever discovered, following Oumuamua in 2017 and 2I Borisov in 2019. But statistical models based on these few detections suggest that dozens or hundreds of interstellar objects should be crossing our neighbourhood at any given moment, most too small or too far from the Sun to develop visible comas that would reveal their presence. Each of these wanderers represents a fragment of a destroyed world, a piece of cosmic history that survived catastrophes we can barely imagine. They're archaeological artifacts from stellar systems that existed when the universe was young, carrying information about galactic conditions from epochs that no other objects can provide. Their surfaces and interiors contain pristine samples of ancient interstellar dust, complex organic molecules that formed under different chemical conditions, and possibly even biosignatures if life emerged in those ancient stellar systems before being extinguished. But 3 Atlas also serves as a sobering reminder of our solar system's ultimate fate. In a few billion years, when our Sun begins its red giant phase and expands to engulf the inner planets, gravitational interactions will destabilize the outer solar system. Comets, asteroids, and possibly even planets will be ejected into interstellar space, becoming ancient wanderers that will puzzle astronomers in distant galaxies long after Earth is consumed by the dying Sun. These future exiles from our solar system will carry evidence of our existence into the cosmic deep. If any artifacts of human civilization survive on the Moon or Mars or in the asteroid belt, they'll eventually become interstellar archaeological sites, drifting through the galaxy as silent testimony that intelligent life once thrived in a solar system long since destroyed. Some distant civilization might intercept one of our ejected comets billions of years from now, and detect chemical anomalies suggesting that industrial processes once occurred in its parent system, just as we're now detecting chemical signatures in 3I Atlas that reveal conditions in an ancient stellar system. The ancient comet's visit was a preview of cosmic timescales that dwarf human understanding, but Webb's surveys revealed objects even more mysterious than time-travelling visitors from dead star systems. Throughout the early universe, scattered like breadcrumbs in a dark forest, 300 enigmatic objects glow with properties so unusual that astronomers can't even classify them into existing categories. 300 mysterious objects are glowing in the early universe, and astronomers can't figure out what they are. James Webb's deep surveys have uncovered a new population of cosmic objects that don't fit into any known category. These little red dots appear as tiny crimson pinpricks of light scattered throughout images of the early universe. But their properties are so unusual, so impossible according to existing models, that scientists are struggling to determine what they're even looking at. Each one is far brighter than it should be given what we know about galaxy and star formation in the universe's youth. They produce enormous amounts of energy through unknown processes, creating a combination of properties that doesn't match any object in the modern universe. Think of them like encountering an item in a video game that doesn't match any category in your inventory system. It's not a weapon, not armor, not a potion, not a crafting material. It just glows with an error message because the game's code doesn't know how to classify it. The mystery begins with their color. In astronomy, red light usually indicates either great cosmological distance or cool temperatures. These objects are definitely distant, existing when the universe was less than 1 billion years old. But they're also incredibly luminous, brighter than early galaxies should be. They're producing enormous amounts of energy that gets stretched by cosmic expansion into the red and infrared wavelengths Webb detects. Using advanced analytical techniques, astronomers at the University of Missouri identified 300 of these enigmatic objects in Webb's data. Each one appears roughly the size of early galaxies based on their angular extent on the sky, but they produce far more light than galaxy formation models predict. If they're galaxies, they're unlike any that exist in the modern cosmos. The objects are so bright that they force scientists to reconsider fundamental assumptions about how galaxies could have formed in the early universe. Traditional models assume the first galaxies grew slowly, accumulating matter through gravitational collapse over hundreds of millions of years. Gas clouds would cool and fragment into stars. Those stars would live, die, and enrich their surroundings with heavy elements. Gradually, over many stellar generations, galaxies would build up their stellar populations and increase in luminosity. The little red dots suggest this gradual process isn't the whole story. Some mechanism was creating massive luminous structures much more rapidly than current theories allow. But here's where the mystery deepens into genuine confusion. When astronomers try to determine exactly what's producing all this light, the answers don't make any sense. Some of the objects appear point-like when analysed at high resolution, suggesting they might be powered by supermassive black holes rather than distributed star formation. Black holes accreting matter create extraordinarily bright emissions from their superheated accretion disks, often outshining entire galaxies despite being concentrated in regions smaller than our solar system. If the little red dots are black hole powered, they'd represent yet another example of supermassive black holes existing far earlier than traditional formation timelines allow. But other little red dots show evidence of extended structure, indicating they might be genuine galaxies undergoing extraordinarily rapid star formation. Their spectral signatures suggest the presence of young, hot stars creating ionized regions throughout the objects. Yet the star formation rates required to explain their brightness are physically extreme, requiring these early galaxies to form hundreds or thousands of stars per year, rates that should consume all available gas in just a few million years. The most disturbing possibility is that these objects represent a completely unknown phase of cosmic evolution. During the universe's first billion years, physical conditions were drastically different from today. Matter was denser, concentrations of dark matter were more pronounced, and the cosmic web of large-scale structure was still forming. Perhaps these unique conditions allowed for types of object formation that simply can't happen in the modern universe. Some of the little red dots show evidence of extremely high-energy processes. They emit X-rays, ultraviolet radiation, and infrared light in patterns that suggest violent, chaotic energy production. Whatever is powering these objects is operating under extreme conditions that push the boundaries of known astrophysics. The energy signatures don't match quiet star formation in spiral galaxies. They don't match the steady accretion signatures of dormant supermassive black holes. They resemble something in between, or perhaps something entirely different. The objects also appear to be distributed randomly throughout space, rather than clustered in regions where early galaxy formation was expected to occur based on simulations of dark matter structure. This random distribution suggests they might represent a fundamental property of the early universe, rather than rare, isolated phenomena confined to specific environments. Bangjang Sun, the graduate student leading the research team at the University of Missouri, emphasizes that even if only a small fraction of these 300 objects are confirmed to be genuine early universe phenomena, they will force scientists to modify existing theories of cosmic structure formation. The sheer number of mysterious objects Webb has found, combined with their unusual properties, suggests that our understanding of the universe's first billion years is fundamentally incomplete. Current cosmological models treat the early universe as a relatively simple system, where gravity slowly assembled structures through well-understood processes. The little red dots suggest the early cosmos was far more complex, hosting processes and object types that our simulations never predicted. They might represent a transitional phase between the smooth, nearly featureless universe that existed shortly after the Big Bang and the structured cosmos filled with galaxies that emerged later, or they might be something even stranger. Some speculative theories propose that the little red dots could be primordial structures that don't fit into categories like galaxy, star cluster, or black hole. They might be dark matter concentrations that somehow emit light through processes we don't understand. They might be topological defects in spacetime, cosmic strings or domain walls where the fabric of reality buckled during phase transitions in the early universe. They might even be gravitational lensing artifacts, where the light from more distant objects gets warped and amplified by intervening matter in ways that create apparent objects that don't physically exist. Confirming the nature of these objects requires extensive follow-up observations, with Webb's spectrograph to measure their chemical composition, temperature, and dynamics. Some of the 300 candidates might be instrumental artifacts or foreground contaminants, objects that appear to be in the early universe but are actually much closer. But preliminary spectroscopic analysis of a subset suggests that many are genuine, early universe objects with properties that defy explanation. The little red dots represent perhaps the most significant observational challenge to cosmology that Webb has revealed so far. They're not isolated anomalies that can be explained by tweaking models or adding minor refinements. They're a population of hundreds of objects whose very existence challenges fundamental assumptions about cosmic evolution. But the mystery of the little red dots pales in comparison to what Webb found when it examined galaxies not across cosmic distances, but across vast regions of the modern universe. Galaxies separated by millions of light years, too distant to have any gravitational influence on each other, are moving in coordinated patterns that suggest something profoundly wrong with our understanding of cosmic structure. 90-minute mark quotable. The universe is spinning, all of it, together. And that means either we're living inside something much larger, or everything we know about cosmology is catastrophically wrong. In what may be James Webb's most mind-bending discovery, astronomers have found evidence that galaxies separated by millions of light years are rotating in synchronized patterns. This cosmic choreography defies our understanding of how structure forms in the universe and raises the disturbing possibility that the entire observable cosmos was born with a preferred direction of rotation. The discovery emerged from observations of 263 galaxies captured during Webb's Advanced Deep Extragalactic Survey. When astronomer Leo Shemiya analysed the orientation and rotation patterns of these distant star systems, he found something that should be impossible according to standard cosmological models: galaxies that are far too distant to have any gravitational influence on each other, separated by voids of intergalactic space that light takes millions of years to cross, are spinning in similar directions. To understand why this is so disturbing, think about cosmic structure formation, like a massively multiplayer online game where thousands of players start in random locations. Each player builds their base independently, with no communication or coordination with other players. After months of play, you analyze the game world and discover that all the bases, despite being built by isolated players who never interacted, are oriented in the same direction. Every entrance faces north. Every defensive tower points east. It's statistically impossible unless some hidden game mechanic coordinated everyone's behavior without their knowledge. That's what Webb discovered with galaxy rotations. These galaxies formed independently, shaped by local gravitational interactions with nearby matter and dark matter. They're separated by distances so vast that the light from one galaxy hasn't had time to reach another since the universe began. They cannot be causally connected. They cannot have influenced each other's formation or evolution. Yet they're participating in the same cosmic dance, rotating in coordinated patterns that extend across regions of space containing thousands of galaxies. The correlation isn't subtle. It's statistically significant to the point where chance becomes an implausible explanation. When Shamir's team analysed the rotation axes of galaxies in different regions of the sky, they found that galaxies in certain cosmic sectors preferentially rotate in specific directions. The effect is subtle on individual galaxies but becomes overwhelming when analysed statistically across large populations. This coordinated rotation violates a fundamental principle of cosmology, called the cosmological principle, which states that the universe should be homogeneous and isotropic on the larger scales. Homogeneous means uniform, the same everywhere. Isotropic means the same in all directions. These properties are cornerstones of the standard cosmological model, supported by decades of observations showing that the universe appears statistically identical, regardless of where you look or which direction you face. But coordinated galaxy rotations introduce anisotropy, a preferred direction that breaks the symmetry the cosmological principle demands. If the universe has a preferred rotation axis, it's not isotropic, and if it's not isotropic, then the standard model of cosmology requires fundamental modification. Leo Shamir identified two possible explanations for this phenomenon, and both are profoundly unsettling for conventional physics. The first is that the universe was born rotating. If the Big Bang itself had angular momentum, a net rotation imprinted on the fabric of spacetime from the very beginning, it could have influenced the formation of cosmic structures billions of years later. Large-scale rotation of the cosmos would create preferred directions that subtly affected how matter collapsed under gravity, biasing the spin directions of galaxies that formed from that matter. This explanation aligns with black hole cosmology, a speculative but increasingly plausible theory suggesting that our entire observable universe might be the interior of a massive black hole within a larger parent universe. If our universe is rotating inside a parent black hole, the rotational patterns Webb observed could be evidence of the parent black hole's spin transmitted across cosmic scales through mechanisms we don't understand. Think of it like being inside a massive rotating space station. You're in the interior, unable to see the outer hull or perceive the station's rotation directly. But if you carefully analyze the motion patterns of objects floating inside the station, you might detect subtle correlations that reveal the station's overall rotation. The coordinated galaxy spins could be analogous, a subtle signature of the larger structure we're embedded within. The second explanation is even more disturbing for conventional cosmology. If the universe wasn't born rotating, then the coordinated galaxy spins suggest that existing theories about how cosmic structure forms are fundamentally incomplete. Some unknown force or field must be operating on scales larger than anything scientists have previously considered, creating correlations across distances where cause and effect shouldn't be able to operate. This unknown force could be related to dark energy, the mysterious entity driving cosmic expansion. If dark energy has directional properties, if it pushes space apart more strongly in certain directions than others, it could create the large-scale flow patterns that bias galaxy formation and rotation. Or it could involve dark matter interacting in ways we haven't discovered, creating cosmic currents that influence how galaxies coalesce and spin. The implications extend far beyond galaxy formation. A rotating universe would have different physical properties than the static cosmos described by standard models. Spacetime itself might have preferred directions, creating asymmetries in physical laws that could affect everything from particle physics to the ultimate fate of the universe. Conservation of angular momentum, one of the most fundamental principles in physics, would need to be reinterpreted for a universe with net rotation. The discovery also raises questions about dark energy's geometry. If the universe has a preferred rotational axis, dark energy's effects might vary depending on direction. Cosmic expansion could proceed faster along the rotation axis than perpendicular to it, creating an anisotropic expansion that violates the cosmological principle. This could explain some of the anomalies Webb has found in cosmic expansion rates, including the Hubble tension. Perhaps we're measuring different expansion rates not because the universe is broken, but because expansion genuinely varies with direction in a rotating cosmos. Perhaps most unsettling is what a rotating universe suggests about our place in the cosmic hierarchy. If our universe is spinning inside a larger structure, it implies that reality extends far beyond the observable cosmos we can study. We might be living inside just one component of an incomprehensibly vast multiverse, where entire universes rotate like galaxies within some higher dimensional space. This hierarchy could extend indefinitely, just as galaxies contain solar systems, which contain planets, which contain atoms, which contain particles. Our universe might be a structure within a larger cosmic system that itself rotates within something even more vast. The coordinated galaxy rotations might be the first direct observational evidence that we're not at the top of the cosmic hierarchy, that our universe is embedded within structures we can never directly observe. The coordinated rotation discovery represents a fundamental challenge to our understanding of cosmic structure formation and the nature of spacetime itself. But the universe's hidden rotations are just one aspect of large-scale, cosmic mysteries Webb is uncovering. The telescope's observations of galaxy clusters and their surrounding environments have revealed violence on scales that dwarf anything we imagined, invisible catastrophes that reshape cosmic structure through forces we cannot see. A black hole is devouring matter 40 times faster than the laws of physics allow, and it's growing at impossible rates. Hidden among thousands of X-ray sources in deep space, James Webb identified a supermassive black hole that's breaking fundamental rules about how quickly these cosmic monsters can feed. The object, designated LID 568, is consuming matter at 40 times its theoretical Eddington limit, a rate so extreme that it challenges our understanding of black hole physics and accretion processes. Every black hole, regardless of size, has an Eddington limit. This maximum feeding rate is determined by a balance between gravity, trying to pull matter inward, and radiation pressure pushing matter outward. When material falls toward a black hole, it doesn't plunge directly across the event horizon. Instead, it spirals inward through an accretion disk, gradually losing energy and angular momentum through friction and magnetic interactions. This accretion process heats the infalling matter to millions of degrees, causing it to emit intense radiation across the electromagnetic spectrum. But here's the problem. That intense radiation creates outward pressure on surrounding matter. Photons carry momentum, and when they collide with atoms in the accretion disk's outer regions, they push those atoms away from the black hole. At a certain accretion rate, the radiation pressure becomes strong enough to blow away any additional matter trying to fall in. This critical rate is the Eddington limit, and it sets the maximum speed at which black holes can grow through normal accretion. The analogy of trying to drink from a fire hose captures this perfectly. There's a maximum flow rate beyond which the pressure becomes so intense that you can't actually consume more liquid. Turn the pressure up higher, and you just get sprayed in the face while consuming the same amount. Black holes face a similar constraint. Beyond the Eddington limit, additional matter gets blown away by radiation pressure before it can cross the event horizon. LID 568 is somehow drinking from 40 fire hoses simultaneously. The black hole is accreting matter at rates that should be physically impossible, consuming material faster than radiation pressure should allow. This super Eddington accretion suggests that something about the environment around this black hole is very different from normal accretion disk models. The discovery required combining Webb's infrared sensitivity with data from NASA's Chandra X-ray Observatory. LID 568 was initially buried among thousands of bright X-ray sources, a cosmic forest where distinguishing individual trees proved nearly impossible with optical telescopes. but Webb's unique infrared capabilities allowed astronomers to identify the faint counterpart emissions that revealed the object's true nature and measure its distance, confirming that it exists just 1.5 billion years after the Big Bang. What makes this black hole's feeding frenzy truly disturbing is what it implies about growth rates and formation timelines. At such extreme accretion rates, ELID 568 could have gained most of its current mass in a single episode of rapid feeding. The black hole appears to be undergoing what astronomers call a super-Eddington accretion phase, consuming enormous amounts of matter in a relatively brief cosmic time span. Think of it like experience point grinding in a role-playing game. Normally you level up gradually by completing quests and defeating enemies one at a time, but imagine discovering an exploit that lets you gain a year's worth of experience points in a single afternoon. That's what ELID 568 is doing, gaining mass at rates that should require hundreds of millions of years in just a fraction of that time. The object exists just 1.5 billion years after the Big Bang, during an epoch when the universe was still in relative infancy. For a black hole to reach supermassive status so quickly, while respecting normal feeding limits, would require starting from impossibly large seed masses. But ELID 568's extreme feeding rate provides a potential solution to this cosmic timing problem. If early black holes underwent similar super-Eddington accretion phases, they could have grown from stellar mass seeds to supermassive monsters in timescales far shorter than gradual Eddington-limited accretion allows. The speed and intensity of material flowing away from the black hole, detected through spectroscopic analysis of emission lines, suggests that substantial portions of its mass growth occurred during similar feeding frenzies. These aren't gradual accretion processes spread over billions of years, but violent consumption events that can increase a black hole's mass by factors of 10 or more in cosmic eye blinks. The physics of such extreme feeding remains poorly understood and deeply mysterious. The black hole must somehow be stabilizing the accretion process despite radiation pressures that should blow away its food supply. Several mechanisms could potentially allow super-Eddington accretion. The infalling matter might be extremely clumpy rather than smooth, with dense clouds plunging through the radiation field too quickly to be significantly affected. The accretion disk might be thick and geometrically complex, with material shielded from direct radiation by the disk's own structure. Or magnetic fields might be channeling matter along specific pathways that bypass regions of intense radiation. Another possibility involves the nature of the matter being accreted. If the material is primarily cold molecular gas rather than hot ionized plasma, it might be more resistant to radiation pressure. Cold gas is denser and less easily accelerated by photon impacts. If ELID 568 is consuming vast clouds of cold molecular hydrogen, it could potentially exceed Eddington limits by a substantial factor. The discovery of ELID 568 suggests that super-Eddington accretion might be a relatively common phase in early black hole evolution. If many young black holes undergo similar feeding frenzies, it would explain how supermassive black holes reach their enormous sizes so quickly in cosmic history. Instead of slow, steady Eddington-limited growth over billions of years, they underwent brief but intense feeding episodes that catapulted them to supermassive status. But this rapid growth mechanism raises disturbing questions about the violence of the early universe. If super-Eddington accretion was common, the cosmos's first billion years must have been dominated by incredibly energetic events, with young black holes consuming matter at rates that release tremendous amounts of energy into their surroundings. This energy output would have affected star formation, galaxy evolution, and the ionization state of intergalactic gas across vast regions of space. ELID 568's impossible feeding rate represents the extreme end of black hole behavior, operating under conditions that push physics to its absolute limits. But even this cosmic glutton pales in comparison to the large-scale violence Webb has discovered operating throughout the universe. Invisible forces are reshaping cosmic structure through processes so destructive they tear entire galaxies apart. We've journeyed through impossible galaxies and premature black holes. We've witnessed feeding frenzies that break the laws of physics and discovered coordinated rotations that suggest the universe itself is spinning. But these phenomena, as disturbing as they are, merely hint at deeper truths about the nature of reality. In this final act, we'll confront the most unsettling implications of Webb's discoveries. We'll explore how magnetic fields throughout the universe form patterns identical to human brain networks. We'll witness dark matter violence tearing apart entire galaxy clusters. We'll encounter gravitational effects so extreme they warp time itself. And we'll confront a terrifying possibility, suggested by all these observations combined, that our entire universe might be the interior of a black hole within a larger cosmos we can never observe. What Webb has revealed isn't just that our models are wrong. It's that reality itself operates according to principles so alien, so fundamentally different from our intuitions, that we might be cosmological children playing with concepts we're not yet equipped to fully comprehend. The final act will challenge everything you think you know about existence. Invisible catastrophes are reshaping cosmic structure through violent processes that leave galaxies shredded and scattered across millions of light years. James Webb has uncovered evidence that dark matter, the mysterious substance comprising 85% of all matter in the universe, participates in violent interactions that can tear apart entire galaxies and reshape cosmic structure on the larger scales. These dark matter catastrophes operate through mechanisms that remain completely invisible except for their devastating effects on normal matter. The evidence comes from Webb's observations of galaxy clusters, regions where hundreds of galaxies are held together by the gravitational influence of massive dark matter concentrations. When these cosmic cities collide, they create some of the most energetic events in the universe, releasing energies comparable to billions of supernova explosions. But Webb's detailed imaging revealed that the violence extends far beyond the visible collision zones. Galaxies located millions of light years from cluster collisions show signs of having been violently disrupted by gravitational forces that can only be explained by dark matter interactions operating on previously unimaginable scales. The telescope detected extensive streams of stars and gas connecting galaxies across vast distances, creating bridge-like structures that span the space between separate galactic systems. These stellar streams represent the torn remnants of galaxies that have been gravitationally shredded by dark matter forces during cluster interactions. What makes this cosmic violence particularly disturbing is its hidden nature. While normal matter interactions create visible fireworks through electromagnetic radiation, dark matter collisions produce no light, no heat, and no electromagnetic signatures whatsoever. Dark matter interacts only through gravity, making these catastrophes completely invisible except for their effects on the matter we can observe. The only evidence of these violent events comes from tracking the motion and distribution of stars and gas, watching how gravitational forces tear them away from their parent galaxies. Webb's infrared sensitivity has revealed the full extent of this dark violence. Faint stellar streams and tidal tails extend for millions of light years around galaxy clusters, creating vast spiderwebs of disrupted matter that previous telescopes were too insensitive to detect. Each stream represents a galaxy that has been partially or completely destroyed by dark matter interactions, its stars scattered across intergalactic space like cosmic debris from a catastrophic collision. Think of dark matter violence like invisible players in a multiplayer game who can interact with visible players but cannot be seen or detected directly. The visible players suddenly get knocked around by forces they can't observe, objects get moved by invisible hands, and structures get demolished by attackers who leave no trace except the destruction they cause. That's what Webb is seeing throughout the universe, galaxies being torn apart by gravitational forces from dark matter concentrations we cannot directly observe. The scale of this destruction suggests that dark matter doesn't simply provide passive gravitational scaffolding for cosmic structure. Instead, it participates actively in reshaping the universe through violent processes that can eject galaxies from their host clusters, strip away their gas supplies, and scatter their stars across intergalactic voids. Galaxy clusters aren't stable structures where galaxies orbit peacefully for billions of years. They're violent arenas where gravitational warfare between dark matter concentrations continuously reshapes the population of galaxies. Computer simulations of dark matter interactions show that these violent events might be fundamental to cosmic evolution. Dark matter particles can undergo gravitational collisions that create shock waves propagating through the cosmic web, affecting galaxy formation across vast regions of space. When galaxy clusters collide, their dark matter halos interpenetrate and interact, creating complex gravitational fields that can fling galaxies away at speeds of thousands of kilometers per second. Perhaps most unsettling is what this hidden violence suggests about the nature of dark matter itself. If dark matter can participate in such energetic interactions, it might have properties beyond simple gravitational attraction. Some models propose that dark matter particles can undergo phase transitions, shifting between different states that affect how they clump and interact. Other theories suggest dark matter might interact through forces we haven't yet identified, creating effects that go beyond pure gravity. The discovery of widespread dark matter violence also affects our understanding of galaxy evolution and the formation of cosmic structure. If galaxies are constantly being disrupted and reformed through dark matter interactions, the universe might be far more dynamic and chaotic than our static models predict. Galaxies might not evolve smoothly over billions of years, gradually accreting gas and merging with neighbours. Instead, they might experience episodic violent disruptions that fundamentally alter their properties on relatively short timescales. These invisible catastrophes represent a fundamental aspect of cosmic evolution that operates completely outside our direct observation, shaping the universe through violence we can only detect through its aftermath. But dark matter violence isn't the only large-scale phenomenon Webb has revealed. Throughout the cosmos, magnetic fields thread the space between galaxies, creating patterns so eerily similar to human brain networks that they force us to question what we think we know about cosmic structure. Reality has an expiration date. The structures we observe, the laws we've discovered, even the fabric of space-time itself might be temporary features of a universe that's fundamentally unstable. Ancient magnetic fields discovered throughout the cosmic web are as complex as human brain networks, and they're older than any known structure in the universe. James Webb has detected evidence of magnetic fields stretching across the largest structures in the cosmos, creating patterns of connectivity that eerily resemble the neural networks found in human brains. These primordial magnetic fields appear to be remnants from the universe's first billion years, shaped by processes during the epoch when cosmic structure was still forming. The discovery emerged from Webb's observations of the cosmic web, the vast network of filaments and voids that organizes matter on the larger scales. Between galaxies and galaxy clusters, thin streams of gas and dark matter create bridges spanning hundreds of millions of light years. These cosmic filaments connect clusters like roads connecting cities, creating a three-dimensional network that fills the universe. Webb found that these cosmic filaments are threaded with magnetic fields of extraordinary complexity. The magnetic field patterns show a level of organization that shouldn't exist in the early universe. Instead of simple uniform fields that would result from random processes, Webb detected intricate networks with nodes, connections, and hierarchical structures that mirror the topology of biological neural networks. The similarity is so striking that researchers are using the same mathematical tools developed to study brain connectivity to analyze cosmic magnetism. Network topology analysis reveals that the magnetic field structure exhibits properties like small world connectivity, where most nodes are not directly connected but can be reached from every other node through a small number of steps. This is the same property that makes the internet efficient, and that characterizes neural networks in human brains. Think of it like discovering that the quest structure in a massive open-world game follows the same mathematical patterns as synaptic connections in the brain. The quest givers and objectives form nodes, and the quest connecting them create a network with properties identical to neural networks. It's not that the game designers consciously copied brain structure. Rather, certain organizational principles might be fundamental to complex information processing systems, regardless of their physical substrate. The cosmic magnetic field networks might represent a similar principle. Certain topologies and connectivity patterns might emerge naturally in any complex system where multiple interacting components organize themselves. The universe's magnetic field structure and the brain's neural structure might both reflect fundamental organizational principles that transcend their vastly different scales and physical implementations. But these ancient magnetic fields raise profound questions about cosmic evolution that go beyond mere mathematical similarity. Standard astrophysical models assume that magnetic fields in space develop gradually as galaxies and stars form. Stellar winds, supernova explosions, and rotating charged particles create and amplify magnetic structures over billions of years. The magnetic fields Webb detected appear to predate this process entirely. The fields show evidence of having influenced early galaxy formation in ways that current theories don't account for. Magnetic pressure and magnetic reconnection events might have shaped how gas collapsed into the first stars, affecting stellar masses, formation rates, and the chemical evolution of early galaxies. If primordial magnetic fields played a crucial role in structure formation, then our models of galaxy evolution, which typically treat magnetic fields as minor secondary effects, are fundamentally incomplete. Perhaps most disturbing is what these brain-like patterns suggest about the nature of cosmic structure formation. The similarity indicates that the universe developed organizational complexity far earlier than scientists believed possible. Instead of simple gravitational collapse, creating cosmic structure through well-understood bottom-up processes, the early cosmos might have operated more like a vast information processing system. Information theory and network science suggest that systems capable of processing information develop specific organizational properties. They form hierarchical structures with hubs and connections. They exhibit small world topology that balances local clustering with global connectivity. They develop feedback loops and emergent behaviors that cannot be predicted from individual components alone. The cosmic magnetic field network displays all these properties. If the universe developed information processing capabilities during its first billion years, it raises profound questions about the nature of physical law and cosmic evolution. Physical processes might not be purely mechanical, driven by forces and particles interacting according to fixed rules. The universe might possess intrinsic tendencies toward complexity and organization that emerge from the structure of physical law itself. The Hungarian physicist Leo Szilard once explored the connection between information and physical systems in his work on Maxwell's demon and the thermodynamics of information. His insights, developed in the early 20th century, suggested that information has physical reality and can affect the evolution of physical systems. The brain-like magnetic networks Webb has discovered might be a macroscopic manifestation of this principle, showing that information processing structures emerge naturally in physical systems, across all scales from neurons to cosmic filaments. The magnetic field networks also appear to be dynamic, with connections forming and breaking across cosmic time. Webb detected evidence of magnetic storms spanning entire galaxy clusters, events that could affect star formation and galactic evolution across vast regions of space. These storms might represent the universe processing information, with magnetic reconnection events analogous to synaptic firings in neural networks. The discovery has implications for our understanding of dark matter and dark energy. Magnetic fields can interact with charged particles in ways that affect how matter clumps together on large scales. If primordial magnetism was more complex and powerful than current models assume, it might explain some of the discrepancies Webb has found in cosmic structure formation. Magnetic pressure might partially offset dark energy's influence in certain regions, creating variations in expansion rates that contribute to the Hubble tension. The brain-like magnetic networks represent a fundamental challenge to our understanding of how complexity emerges in the universe. If such sophisticated organizational structures existed in the cosmos's youth, it suggests that the universe has intrinsic tendencies toward complexity that we've never properly recognized. These primordial magnetic fields might be evidence that physical processes, at their deepest level, are not random or mechanical but follow organizational principles that favor the emergence of structure and complexity. But magnetic field networks are just one example of the large-scale structure that Webb's observations are forcing us to reconsider. At the very heart of our galaxy, a supermassive black hole pulses with irregular rhythms that suggest unknown physics operating at the edge of spacetime where our understanding of physical law breaks down completely. Magnetic fields older than galaxies form patterns identical to human brain networks, suggesting the universe itself might process information through structures we're only beginning to recognize. A supermassive black hole at the center of our galaxy is pulsing with irregular rhythms that suggest unknown physics operating at the edge of space-time. Sagittarius A, the 4 million solar mass black hole, anchoring the Milky Way's center, has been quietly surprising astronomers for decades. But James Webb's continuous monitoring revealed something unprecedented. The cosmic monster exhibits erratic brightness fluctuations that resemble a heartbeat. with no discernible pattern. Using Webb's near-infrared camera, researchers observed Sagittarius A for 48 hours, spread across multiple sessions throughout 1 year. What they discovered was a black hole in constant flux, with its accretion disk producing continuous but chaotic series of brightness changes punctuated by sudden dramatic flares. The observations showed constantly changing, bubbling brightness across the black hole's event horizon region, then massive bursts of radiation would suddenly erupt from the accretion disk before calming down again. These flares appear completely random, defying every attempt to find underlying patterns or periodicities. Some last minutes, others hours. Some increase brightness by factors of 10, others by factors of 100 or more. The intervals between flares vary from hours to days with no consistent timing. It's like watching a heart that beats randomly, sometimes racing, sometimes slowing, never following a predictable rhythm. Farhad Yousefzadeh, the Northwestern University professor leading the research, described the behavior as unlike anything previously observed in supermassive black holes. The team found no patterns in the activity, suggesting that the processes driving these brightness changes operate according to physics that current models don't fully capture. Think of observing Sagittarius A like monitoring server behavior in an online game. Normally you'd expect relatively stable performance with occasional spikes when many players log in simultaneously. But imagine the server load varying wildly and randomly, spiking and dropping with no correlation to player activity, time of day, or any other identifiable cause. That unpredictability would suggest that something fundamentally wrong or unknown was affecting the server's operation. That's what astronomers see with Sagittarius A. Two mechanisms appear to be creating this cosmic heartbeat, but neither fully explains the chaotic nature of the variations. Short-term fluctuations likely result from turbulence within the accretion disk, where magnetic field interactions compress plasma and create temporary flashes of radiation. Think of it as cosmic lightning occurring in the superheated gas spiraling toward the black hole's event horizon. But the larger flares suggest something more dramatic. These massive brightness increases might result from entire chunks of matter, perhaps fragments of disrupted stars or gas clouds, crossing the black hole's photon sphere. The photon sphere is the region where light itself begins to orbit the black hole due to extreme spacetime curvature, before either escaping or falling past the event horizon forever. When matter crosses into the photon sphere, it experiences gravitational and tidal forces strong enough to shred it completely. Any structure it possessed, whether it was a coherent gas cloud, an asteroid, or even a planet, gets torn apart on subatomic scales. This violent disruption releases tremendous amounts of energy in sudden bursts that could explain the large flares Webb observes. The irregular nature of these events indicates that Sagittarius A is more active than astronomers previously realized. Instead of the relatively quiet, slowly feeding monster described in textbooks, feeding primarily on thin hot gas from stellar winds, the Milky Way's central black hole appears to be in a constant state of low-level violence. It consumes matter in unpredictable episodes, with each feeding event producing brightness variations that depend on the properties of the specific material being consumed. What makes this behavior truly disturbing is its implications for black hole physics near the event horizon. The brightness fluctuations originate from regions where spacetime is severely distorted by gravity, creating conditions where matter and energy behave according to principles that push general relativity to its limits, and potentially beyond. Near the event horizon, gravitational time dilation becomes extreme. Clocks in the accretion disk near the photon sphere run significantly slower than clocks far from the black hole. If you could somehow hover just above the event horizon and watch the distant universe, you'd see events unfolding at dramatically accelerated rates. Stars would be born, live their lives, and die in what appears to you as fast-forward footage. Conversely, distant observers watching you would see your movement slowed to nearly frozen stillness. This time, dilation affects the accretion process itself. Matter spiraling inward toward the event horizon appears from distant perspectives to slow down and freeze as it approaches the horizon, creating a bright shell of radiation that never quite crosses into the black hole from external viewpoints. Yet from the perspective of the infalling matter itself, The crossing occurs in finite time. This paradox, where different observers see fundamentally different versions of the same events, lies at the heart of the black hole information paradox. The chaotic nature of the brightness changes suggests that quantum effects might be playing a role in black hole accretion processes. Near the event horizon, the boundary between classical physics described by general relativity and quantum physics becomes blurred. Virtual particle pairs constantly pop into existence and annihilate in the quantum foam pervading all space. But near a black hole's event horizon, these virtual pairs can be split, with one particle falling into the black hole while the other escapes as Hawking radiation. This process should cause black holes to gradually evaporate over incomprehensibly long timescales. For a black hole the mass of Sagittarius A, complete evaporation would require more than 10 to the 100 years, far longer than the universe's current age. But the quantum processes operating near the event horizon might affect accretion as well as evaporation, creating unpredictable fluctuations in how matter falls inward and how energy gets released. The heartbeat pattern also raises profound questions about what happens to information that falls into black holes. Quantum mechanics demands that information cannot be destroyed. Every physical process must be reversible in principle, even if the reversal is impractical, but black holes appear to destroy information. Matter carrying specific quantum states falls past the event horizon and disappears from the observable universe. The black hole's mass increases slightly, but all the detailed information about the infallen matter's quantum state seems to vanish. If the accretion disk's behavior is truly random, it might indicate that black holes do destroy information in ways that violate fundamental principles of quantum mechanics. The irregular brightness changes could be evidence that quantum information is being scrambled or lost as matter crosses the event horizon, creating genuinely random rather than merely chaotic behavior. Alternatively, the apparent randomness might be an illusion created by our limited observational capabilities. The brightness variations might follow deterministic rules that depend on the detailed quantum states of infalling matter. From our distant external perspective, unable to resolve individual particles or their quantum properties, the process appears random. But in principle, with complete information about the system's quantum state, the flickering might be entirely predictable. Sagittarius A's irregular pulsing represents our closest laboratory for studying physics, operating under the most extreme conditions the universe can create, where gravity becomes so strong that spacetime itself begins to break down, and quantum effects begin to dominate over classical processes. But the black hole at our galaxy's centre is just one example of extreme gravitational phenomena Webb has uncovered. Throughout the cosmos, gravitational fields so intense they warp time itself are creating effects that challenge our understanding of causality and the nature of reality. We live inside a black hole. The expansion we observe, the structures that form, the very flow of time itself, all might be features of our descent through a cosmic event horizon we crossed 13.8 billion years ago. A distant galaxy is bending spacetime so severely that it appears in multiple locations simultaneously, creating gravitational effects that push general relativity to its theoretical limits. James Webb discovered a galaxy so massive and dense that its gravitational field creates multiple images of background galaxies, each showing the same star system at different points in its evolutionary history. This extreme gravitational lensing effect demonstrates space-time curvature operating at levels that test Einstein's general relativity under the most extreme conditions. Strong gravitational lensing occurs when an object becomes so massive that its gravity bends the fabric of space-time like a cosmic magnifying glass. Light from more distant objects follows these curved paths, creating distorted or multiple images that can appear in surprising locations across the sky. But this particular galaxy, acting as a gravitational lens, creates effects far more extreme than anything previously observed. Webb detected at least 4 separate images of the same background galaxy, each magnified by different amounts and showing the star system at different epochs in its history. The gravitational field is so powerful that light takes different amounts of time to travel along each curved path, creating a time delay effect. This time delay means that astronomers are essentially watching the same galaxy's history unfold in multiple versions simultaneously. One image shows the galaxy as it appeared 800 million years ago. Another reveals its structure 1 billion years in the past. A third captures it at an intermediate epoch. The lensing galaxy has created a cosmic time machine that displays stellar evolution across multiple time periods in a single observation. Think of it like lag in an online multiplayer game creating ghost images of players. Your character appears in multiple locations on other players' screens because the network latency varies, causing updates to arrive at different times. The gravitational lens creates a similar effect, but with actual physical processes rather than network delays. The light paths have different lengths and experience different time dilation effects, causing images from different cosmic epochs to arrive at our telescopes simultaneously. What makes this discovery truly disturbing is the implied mass distribution of the lensing galaxy. To create such extreme spacetime curvature, the galaxy must contain dark matter concentrations far denser than current models predict. The dark matter appears to be clumped into structures that challenge our understanding of how these mysterious particles interact and organize themselves. The lensing effects also reveal substructure within the dark matter distribution that shouldn't exist according to standard cosmological models. Instead of smooth dark matter halos surrounding the galaxy, as simulations predict, Webb detected evidence of dark matter, clumps and voids that suggest complex internal dynamics operating through unknown mechanisms. These dark matter substructures might represent remnants of smaller dark matter concentrations that merged to build the lensing galaxy's halo. Or they might indicate that dark matter particles interact with each other more strongly than the simplest models assume, allowing them to clump on smaller scales than pure gravitational dynamics would create. Some theories propose that dark matter might undergo phase transitions or form bound states under certain conditions, creating structures with properties beyond what simple collisionless cold dark matter models predict. The time delay measurements between different lensed images provide direct observational evidence of spacetime curvature operating according to general relativity's predictions. But the extreme nature of the lensing pushes these effects into regimes where quantum gravitational effects might begin to influence classical spacetime geometry. At the most extreme curvatures, where gravitational fields approach the Planck scale, quantum mechanics and general relativity must somehow merge into a theory of quantum gravity that we don't yet possess. Perhaps most unsettling is what this discovery suggests about the prevalence of such extreme gravitational environments in the universe. If one galaxy can create space-time curvature this severe, there might be numerous other cosmic regions where space and time are distorted beyond our current ability to model or understand. These regions might be natural laboratories where quantum gravitational effects become observable, offering glimpses into physics beyond the standard model and general relativity. The multiple images also reveal that the lensed galaxy itself is undergoing rapid evolution, with star formation rates changing dramatically between the different time epochs visible in each image. This provides unprecedented insights into how galaxies evolve during their most active phases, allowing astronomers to watch stellar populations change over hundreds of millions of years compressed into a single observation. But gravitational lensing effects, as extreme as they are, represent just one way that massive objects reshape the geometry of spacetime. Throughout the universe, Webb has discovered evidence that spacetime itself might be fundamentally unstable, prone to breaking down under conditions that exist naturally in the cosmos. Evidence is mounting that reality itself breaks down at cosmic scales, revealing fundamental cracks in the fabric of spacetime that challenge our most basic understanding of physics. James Webb's most disturbing discovery might not be any single object, but rather the accumulating evidence that spacetime itself becomes unstable under extreme conditions found throughout the cosmos. The evidence comes from multiple sources across Webb's surveys. Gravitational lensing effects around some massive objects don't follow precise general relativistic predictions, showing small but persistent deviations that could indicate spacetime structure breaking down under extreme gravitational stress. These anomalies appear near black holes, in galaxy cluster cores, and around other massive cosmic structures where spacetime curvature reaches extreme values. Quantum mechanics predicts that spacetime at the smallest scales should be foamy and chaotic, with virtual particles and energy fluctuations creating turbulent quantum foam that underlies smooth classical geometry. But Webb's observations suggest that this quantum foam might bubble up to macroscopic scales under certain extreme conditions. The telescope has detected unexplained energy emissions from regions where quantum effects shouldn't be observable, including mysterious radiation signatures from black hole event horizons and anomalous heating in galaxy cluster cores. These phenomena might represent quantum foam breaching into classical spacetime during particularly violent cosmic events. Perhaps most unsettling are Webb's observations of what astronomers call cosmic strings, hypothetical one-dimensional defects in spacetime that could have formed during the universe's earliest moments. If these structures exist, they represent fundamental cracks in reality itself, places where spacetime is literally torn or folded in ways that violate our understanding of cosmic geometry. The telescope has identified several candidates for cosmic string signatures, including gravitational lensing patterns that can't be explained by any known distribution of matter or energy. These observations suggest that the universe might contain permanent scars from its violent birth, defects that persist as vulnerabilities in spacetime structure. Webb has also found evidence of vacuum decay events, regions where the quantum vacuum appears to have transitioned to lower energy states through processes that release enormous amounts of energy. These events could represent fundamental phase transitions in the structure of reality itself, moments where space-time shifts between different configurations with different physical properties. The accumulating evidence suggests that the universe operates closer to the edge of physical stability than previously believed. Under extreme conditions involving massive gravitational fields, high energy densities, or exotic matter states, the fundamental structure of spacetime might become unstable, creating breakdowns in the classical smooth geometry that general relativity describes. These quantum foam breaches have profound implications for our understanding of cosmic evolution and the ultimate fate of the universe. If spacetime can become unstable under conditions that exist naturally in the cosmos, it raises questions about whether reality itself might be temporary and fragile, potentially vulnerable to catastrophic phase transitions that could alter the laws of physics across vast regions of space. The discoveries also suggest that the boundary between quantum mechanics and general relativity might be more porous than theoretical physics predicts. Quantum effects might influence cosmic-scale phenomena in ways we've never recognized, while gravitational effects might penetrate down to quantum scales, creating a regime of physics that merges both theories in ways we don't yet understand. But all of these unsettling discoveries, from coordinated galaxy rotations to quantum foam breaches, point toward one terrifying conclusion that unifies them all. A conclusion so profound and disturbing that it forces us to reconsider the very nature of existence itself. The coordinated rotation of galaxies, the impossible expansion rate contradictions, the premature formation of massive structures, the quantum instabilities in spacetime itself. Every anomaly Webb has discovered, every impossible object it has found, every law-breaking phenomenon it has revealed, they all point toward one unified explanation, an explanation so disturbing that it challenges everything we think we know about the nature of reality. We might be living inside a black hole, not metaphorically, not as an analogy, literally. In our entire observable universe, everything we can see from the cosmic microwave background to the most distant galaxies, might be the interior of a massive black hole, existing within a larger cosmic structure that we can never observe or communicate with. This black hole cosmology theory explains many of Webb's most puzzling observations simultaneously, while creating a framework that unifies phenomena that seem unrelated in conventional cosmology. The coordinated galaxy, rotations that defy the cosmological principle, would result naturally from our universe inheriting angular momentum from the parent black hole that contains us. If we're inside a rotating black hole, every structure that forms within it would be influenced by that rotation, creating preferred directions and coordinated spins across cosmic scales. The expansion rate contradictions that have created the Hubble tension would emerge from our motion through curved spacetime inside the black hole. Different measurement techniques might be detecting different aspects of this motion, creating apparent contradictions that result from viewing the same phenomenon from multiple perspectives. We're not measuring two different expansion rates. We're measuring different components of our trajectory through the parent black hole's interior geometry. The theory suggests that what we call the Big Bang wasn't an explosion of matter and energy from a singular point into empty space. It was our universe crossing the event horizon of a massive black hole in a higher dimensional space. From our perspective inside the black hole, This crossing appears as cosmic expansion. The metric of spacetime inside a black hole's event horizon is such that the radial coordinate becomes time-like and the time coordinate becomes space-like. This means that moving forward in time necessarily means moving inward toward the black hole's center. We experience this inward motion as the expansion of space. From the perspective of the larger universe outside, we're falling toward the black hole's singularity in a process that will take infinite time due to gravitational time dilation near the event horizon. But from our internal perspective, finite time has elapsed since we crossed the horizon, time we interpret as the 13.8 billion year age of our universe. Webb's discovery of primordial black holes that predate star formation fits perfectly within black hole cosmology. These ancient monsters could be smaller black holes that existed in the parent universe before we crossed the event horizon. They would appear in our cosmic history as primordial objects that formed before normal matter could collapse into stars, explaining how supermassive black holes reached enormous sizes in the universe's youth. The coordinated galaxy spins make perfect sense if our universe inherited rotational momentum from a spinning parent black hole. A rotating black hole has an axis of rotation that defines preferred directions in its interior geometry. Structures forming within this geometry would naturally be influenced by the rotation, creating the large-scale alignments that Webb observes. Even the vacuum energy problem and dark energy find natural explanations in black hole cosmology. The energy density we attribute to dark energy might actually be a manifestation of the negative energy that exists inside black hole event horizons. In the parent universe's perspective, matter crossing the event horizon gains negative energy relative to infinity. From our internal perspective, this negative energy appears as a positive cosmological constant, driving accelerated expansion. The timeline contradictions and rapid structure formation that have puzzled cosmologists could result from differences between coordinate time inside the black hole and proper time experienced by structures. The interior geometry of a rotating black hole is extraordinarily complex, with different regions experiencing different time dilation effects. Regions closer to the rotation axis might experience time differently than regions near the equatorial plane, potentially explaining why some structures seem to form faster than physics allows. If black hole cosmology is correct, it means that everything we can observe from the cosmic microwave background to the most distant galaxies detected by Webb exist within the event horizon of an incomprehensibly massive black hole. We are forever separated from the larger universe that contains us, unable to communicate with or affect anything outside our cosmic prison. The theory also suggests that black holes throughout our universe might contain entire universes of their own, creating a nested hierarchy of cosmic structures where each black hole serves as a gateway to a complete cosmic realm with its own physics, evolution, and potentially life. Every stellar mass black hole formed from a collapsed star might contain a universe with its own galaxies, stars, and possibly civilizations. Every supermassive black hole at a galaxy center might contain a cosmos filled with billions of galaxies. This creates an infinite hierarchy extending in both directions. We might be inside a black hole that itself exists within a larger black hole, nested like Russian dolls through infinite levels of reality. Simultaneously, every black hole in our universe might contain universes that themselves contain black holes, extending the hierarchy downward without limit. The implications are profound and deeply unsettling. If we're inside a black hole, then general relativity predicts that we're necessarily falling toward a singularity at the center. The expansion of space we observe might be the geometric signature of this infall. Eventually, all matter in our universe will reach the central singularity, where densities become infinite, space-time curvature becomes infinite, and the laws of physics as we understand them break down completely. But the timeline for reaching the singularity depends on the properties of the parent black hole. For a supermassive black hole with mass billions of times greater than our observable universe's mass, the journey from event horizon to singularity could take trillions of years of proper time. We might have incomprehensibly long futures ahead of us before the final collapse, or the interior structure might be more complex than simple models predict. Rotating black holes have inner horizons and exotic geometric structures that could fundamentally alter the path toward the singularity. Some solutions to Einstein's equations suggest that the interiors of rotating black holes might contain passages to other regions of spacetime or even other universes, creating a cosmic network where black holes serve as bridges connecting different realms of reality. The black hole cosmology theory transforms our understanding of cosmic significance and our place in the broader structure of reality. What we call the universe might be just one bubble in an infinite multiverse of black hole universes, each containing its own physics, laws, and possibilities. We're not observing the totality of existence, but rather one local pocket of a vastly larger and more complex reality. This realization should be humbling. Everything humanity has ever observed, every astronomical measurement we've ever made, every cosmological theory we've developed, applies only to the interior of one black hole. The larger universe that contains us operates according to laws we cannot observe and possibly cannot comprehend. Our physics might be local, applicable only within our particular black hole universe, while fundamentally different physics govern the parent cosmos. Yet even this disturbing possibility doesn't fully capture the strangeness of what Webb has revealed. The telescope's discoveries have shown us that reality is far more alien, far more unstable, and far more incomprehensible than we ever imagined. We're not just living in a black hole. We're living in a universe where the laws of physics break down under extreme conditions, where space-time itself can become unstable, where quantum effects operate on cosmic scales, and where the boundary between possible and impossible dissolves into uncertainty. The journey James Webb has taken us on isn't just a tour of astronomical discoveries, it's a descent into cosmic horror that reveals the fragility and strangeness of reality itself. We started with impossible galaxies and contradictory expansion rates. We descended through naked black holes and coordinated galaxy rotations. We witnessed quantum foam breaching into classical spacetime and magnetic fields, forming brain-like patterns across the cosmos. Every discovery challenged not just our models, but our most fundamental assumptions about how the universe works. We learned that galaxies can form faster than physics allows. We found black holes that predate the stars they should have formed from. We discovered planets broadcasting radio signals into the void and atmospheres that shouldn't exist around hellish worlds. We watched dark matter violence tearing apart galaxies in processes we cannot see. We witnessed gravitational effects so extreme they create multiple images of the same galaxy across different epochs of time. We found evidence that spacetime itself might be fundamentally unstable, prone to quantum breakdowns under conditions that exist naturally throughout the cosmos. And we confronted the possibility that explains all these anomalies simultaneously, that our universe might be the interior of a black hole, that everything we observe exists within a cosmic prison from which we can never escape, that the expansion we interpret as the growth of space might be our inevitable fall toward a singularity where physics breaks down completely. The discoveries James Webb has made don't just expand our knowledge, they reveal how little we actually understand about the cosmos we inhabit. Despite centuries of astronomical progress, despite our sophisticated theories and powerful technologies, we are cosmological children playing with concepts we're not yet equipped to fully comprehend. The universe Webb reveals is not the orderly, predictable cosmos described in textbooks. It's not a place designed for life or structured for our comprehension. It's a violent, chaotic arena where reality itself can break down, where the impossible becomes routine, and where every answer raises deeper questions about the nature of existence. Perhaps most unsettling is the realization that these discoveries represent only what we've found so far. Webb will continue operating for years, peering ever deeper into the cosmic abyss. What other impossible objects will it discover? What other fundamental laws will it reveal to be broken? What other unsettling truths about reality await in the depths of space and time? We live in an era of cosmological crisis. The models we relied on are shattered. The assumptions we made are violated. The universe has revealed itself to be far stranger than we imagined, and we must confront the uncomfortable truth that our understanding of reality might be fundamentally incomplete. But perhaps that's the most important lesson Webb can teach us. The universe doesn't owe us comprehensibility. Reality operates according to its own logic, following principles that might be fundamentally alien to human intuition. Our survival and success as a species depends not on clinging to comfortable assumptions, but on adapting our understanding to match the cosmos as it actually exists, however disturbing that reality might be. The universe James Webb has revealed is strange, violent, and often incomprehensible, but it's also the only reality we have. And understanding it, no matter how much that understanding challenges our preconceptions, represents our best hope for navigating the cosmic future that awaits. We are creatures of a universe that might be falling toward oblivion inside a black hole, but we are also creatures capable of comprehending that possibility, of questioning our place in reality, and of continuing to explore despite the terrifying truths we might uncover. That capacity for wonder, for questioning, for seeking understanding, even in the face of cosmic horror, that might be the most remarkable phenomenon in the universe. And that perhaps makes the journey worthwhile, regardless of where it leads.